All right, so welcome to Math 383 Complex Analysis. This is lecture 11. And so what we're going to be doing today is we're going to be discussing, at least beginning to discuss, the complex logarithm. Before we do that, I'm going to say a few brief words about the characterization of meromorphic functions. The book is actually pretty readable here. I did it last time, so you can watch the first 10 minutes or so from that class. There's just too many topics to cover in this course to cover everything. And so if you want, you can watch the 10 minutes from last time, you can read the book. It's not something we're going to use too much. We will talk about the argument principle, and we will see one of the beautiful consequences of the argument principle, which is Rouche's theorem. And then we will talk about some of the incredible consequences of Rouche's theorem. Now, if you want, you could say these are consequences of the argument principle, but this way Roushay gets credit. We will just state a few of them today, but we will do one of them, which is a proof of the fundamental theorem of algebra without using Liouville. And then I want to do another integration example. I want to just really drive home how to do these integrals. And so we'll do another trig integral. Some general items to be thinking about during today's lecture is how do we generalize objects that we understand to other settings. A lot of it is getting Pavlovian responses. When you see something, there should be certain natural instincts. So anybody who's taken a class with me, what's the first thing that's come to your mind? Logs. Logs. If you see a product, take a logarithm. Now, unfortunately, in complex analysis, the logarithm doesn't quite exist as well as it does in real analysis, so taking logarithms is a little bit harder. So we'll have to generalize the logarithm. That's not a big deal. Continuous discrete functions are. So I have a function that's continuous, and it takes on a discrete set of values. What can you tell me about it? Yes, it's constant, right? It's a very fancy way. So if I give you a holomorphic function that takes on only, say, integer values, and its effect doesn't even have to be holomorphic, it just has to be continuous, you now know it has to be constant. It is amazing how powerful that observation is. Thoreau is the patron saint of mathematics with his wonderful advice, simplify, simplify, which of course could be simplified to simplify, but then it doesn't have quite the same impact. Where did he write this for cultural extra credit? Walden, excellent. Next thing is the value of multiple proofs. There are many different ways of proving results. We're going to see another proof today of the fundamental theorem of algebra. It's useful to have multiple proofs just in case something is wrong, in case there was an assumption you forgot about. But sometimes different proofs highlight different aspects that generalize better. 2 summers ago, I had a small student looking with me on some problems in additive combinatorics, and she was trying to generalize to several dimensions a result from a previous small in 1 dimension. And unfortunately, the argument just didn't generalize. And eventually I told her, well, you know what? We weren't the first people to look at this. There's an older paper that uses a different technique and doesn't get quite as good of a result, but maybe that generalizes better. And it turns out that that was the case. And that was the argument that ended up winning the day. And so it's very valuable to have multiple ways of doing things to just keep in mind how you might want to approach things. Right? And then the last is the idea of a deformation. We've already talked a little bit about this in terms of what do we mean by a nice region where we can use Cauchy's formula. We mean essentially a region where we can deform one curve continuously to the other. And again, if I have an annular ring and I'm missing the center, I can't deform, say, something going above to something going below. And that's really the key idea behind these proofs. And we will be seeing that again today. All right. So I'm not going to say too much. This is just more for completeness, so it's at least in the slides. So what does it mean for a function to be meromorphic? It means we have a sequence of points z0, z1, z2, such that the function is holomorphic if we remove those points. And then it has poles at those points. And then we have to be a little bit careful about what do we mean about what's going on at infinity. We're not going to do too much in this class on it. Basically, anybody here do any class on differential geometry? All right, so if you're familiar with like a chart system and choosing different charts, that's essentially what we're doing here. We let big F of z equal f of 1 over z. I actually don't like this notation. Why do I not like this notation? Yeah, it looks like it just got integrated. It didn't, but it looks like it. And so we say we have a pole at infinity if when we flip things like this, we have a pole at the origin. Okay, and so the theorem is that meromorphic functions in the extended complex plane, so this is including now this point at infinity, and to understand the point at infinity, you look at your function not f of z, but f of 1 over z. And when you look at f of 1 over z, as z goes to 0, that's the same as f of z with z going to infinity. And so this allows us to just localize in terms of what's going on. It basically says that if you're meromorphic in the extended complex plane, so in the plane as well as this point at infinity, you have to be a ratio of 2 polynomials. Why do we care about something like this? It turns out it's extremely useful to be able to classify things. So we actually already talked about the classification of something earlier today. Continuous discrete valued functions. They're constants. It's amazing how much power that is. In number theory, there's something called modular forms, and you can look at the dimension of spaces. It turns out some of these spaces are one-dimensional. Oh, well, if it's one-dimensional, then everything must be a multiple of one fixed form. And so if you're trying to prove something holds, well, if I know it holds for this form, and the space is one-dimensional, then anything else is just a constant times this. We'll see this again and again in the semester. We'll talk about this in greater detail when we get to the Riemann mapping theorem, that if we have a nice way of classifying objects, that often helps in the analysis. And so it's just nice to know what can functions look like that are meromorphic. And so I'm not going to go into the details. Again, you can see the notes. Basically, what you do is at every point where you have a pole, you write your function as the principal part, which has the 1 over z minus z naught to various powers, but only finitely many of these, then plus a holomorphic part. You do the same thing at infinity. You basically subtract off all the principal parts, and you're left with something that's entire and bounded. What must be true if you're entire and bounded? Constant. So then if it's constant, you bring everything over to the other side, and then you have a bunch of fractions, and when you add a bunch of fractions, you get a rational. You'll get ratio rational polynomials. So this is the quick high-level sketch as to what's going on. All right. So let's talk a little bit about the logarithm. Yes.
The morphic functions can only have finitely many.
Correct.
Powers.
You can only have finitely many poles. All right. So let's talk a little bit about trying to generalize the logarithm. When you do the standard logarithm, what numbers can you take logarithms of? Positive. So we initially could only do logs of positive numbers. We could write a complex number z as x plus iy, or as r e to the I theta. Which do you think might be better for logarithms? Why? Because it has an e. Good. So if we're doing logarithms, the log is related to e, so putting an e in is pretty good. Why else is r e to the I theta? It's a product, right? Log loves products. The sum, no. But products of things, absolutely. So maybe let's try the log of r e to the I theta is the log of r plus the log of e to the I theta. And then just using the fact that we have an e, what would you decide to have the log of e to the I theta be? Yeah. And if I asked you, what would you choose to have the log, the derivative of a product, you'd say the derivative of the product is the product of the derivatives. These are natural things to try. We could then just see, do they work? What are the consequences of trying something like this? Well, what if I give you z is e to the 3 pi I over 2 equals w, then what does zw equal? So if z and w are both e to the 3 pi I over 2, what's the product? I'm sorry? Negative 1. And how do I want to write negative 1? I can write that as e to the I pi. So if I try to take the log of zw versus the log of z plus the log of w, I would get the log of e to the I pi versus the log of e to the 3 pi I over 2 plus the log of e to the 3 pi I over 2. So I get I pi versus 3 pi I over 2 plus 3 pi I over 2 equals 3 pi I equals pi I plus 2 pi I. So we see that there are some issues. And the problem is we can't really define the logarithm on the entire complex plane. If we start over here at theta equals 0, and we try to come all the way around to theta equals 2 pi, as we start getting closer and closer and closer, we have an issue. Are we taking e to the 0 or e to the 2 pi I? And using hope for the logarithm, we see that it's not going to match up. So what this tells us is that we're going to have to be a little bit careful in how we define the logarithm. Okay. And again, it's because there's more than one way to write a number as r e to the I theta. We don't have a unique decomposition. We do have a unique decomposition if we restrict theta to being 0 to 2 pi, we do not include 2 pi. And so this is starting to give us this idea of maybe we can start continuing things, but we can't go all the way around. And there's going to become obstructions. We will talk in much greater detail about the logarithm in the next lecture. This is just to show us that we have to be very careful. So unfortunately, this naive notion is not going to work. So how do we generalize the logarithm? Okay, so what we can do is let's think back. If I take a product and I take the derivative and divide it by the original, what do I get? Well, the derivative of f1, f2 is f1 prime f2 plus f2, I'm sorry, plus f1, f2 prime. When I divide by f1, f2, I get f1 prime over f1 plus f2 prime over f2. This is the same if I had instead 3 functions by induction, it would just be the sum of fk prime over fk. Why am I doing something like this? Well, let's consider d by dx of the log of f of x. So what rule would you use to take this derivative? Chain. So the derivative of log is going to be 1 over f of x times f prime of x, or f prime of x over f of x. This is the logarithmic derivative. Whenever you see a function in complex analysis, one of your Pavlovian responses should be take the logarithmic derivative and counter-integrate. Oops. So Pavlovian response. Take the logarithmic derivative of f, do a contour integral. We will see that there are a tremendous number of problems where this is a useful thing to do, and we can get a tremendous amount of information from something like this. Okay, so why is this somewhat similar to the logarithm? What's the connection? Yeah, so we basically have product coming into a sum. So we see similarity, product to a sum. And really, when you look at f prime over f, there's a log in the background, right? We have a hidden log when we study f prime over f, right? Where's the hidden log? This is because this is just equal to the derivative of the log of f of x. But f prime over f doesn't involve logarithms. F prime over F just involves our function and its derivative. So it's a nice way to connect the two logarithms without having the logarithm explicitly there. And so this might be a really good object to study. So again, what I want to try to do with the class time is I want to try to really emphasize certain key points and leave the more standard calculations to the book. If you have any questions about this, just email me. Always happy to try to find a time to meet and chat. So let's see some consequences of this. So imagine I have my function f of z is z minus z naught to the n times g of z. And here I'm going to assume, g of z equals 1 plus maybe a1 z minus z naught plus dot, 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 dot. So I'm writing, g of z as something nice. What I'm doing is I'm pulling out as many powers of z minus z naught as I can for my function f. If it's a 0, then n is going to be a positive integer. If it's a pole, n is going to be a negative integer. And if I look at the logarithmic derivative, if I look at f prime over f, well, if I just use the rule from the previous page, the derivative of f1 f2 prime over f1 f2 is just f1 prime over f1 plus f2 prime over f2. So if I just do the algebra like that, I get, n over z minus z naught. So here, this would be the f1 of z, and this would be the f2 of z. And then we would just use f prime over f is f1 prime over f1 plus f2 prime over f2. And so if I use that relation, well, it's very easy to take the derivative of f1. F1 is just z minus z naught to the n. So when I take its derivative, I'll get n z minus z naught to the n minus 1 over z minus z naught to the n. That's going to be the n over z minus z naught. The other one is a little bit more involved, but the key thing to note is g of z is holomorphic at z naught, and it has a constant term of 1. So when I look at the derivative, g prime over g, it's still going to look nice. It's not going to have a pole. So g of z is going to be g prime of z over g of z. G of z naught equals 1, so no pole. Thus, it's holomorphic at z naught. So in a small neighborhood of z naught, if I look at f prime over f, it's essentially n over z minus z naught. So what would you get if you did 1 over 2 pi I, the integral over a small circle centered at z naught of f prime of z over f of z dz? What would you get? It would just be n. A small circle about z naught. Why? Yeah. So, yeah, it's just the residue of f prime over f at z naught. And that's residue is just n. So what's nice about this is, if n is a positive integer, f is holomorphic. But now here's an integral of f that's not 0. If n is a negative number, then I already had a pole of f, and if I integrated f, I might have something that's non-zero. But this is a way to get an integral that is not necessarily 0. If everything is 0, it's going to be hard to get a lot of information. So the idea is, by studying f prime over f, I might be able to get something of use. All right. So I pasted this from the book. I had some trouble when I was looking at my notes. Suppose f is meromorphic in an open set containing a circle C and its interior. If f has no poles and never vanishes on C, then the integral of f prime over f, with the 1 over 2 pi I, is the number of zeros of f inside C minus the number of poles of f inside C, where the zeros and poles are counted with their multiplicity. But this makes no sense, Because we said if f has no poles, so why would I be subtracting off the number of poles? Yes, it's f has no poles on C, and f never vanishes on C. And so can somebody tell me why we have some wildlife on the bottom? We have a cute little panda eating and getting ready to defend itself. Why is there a panda? Yes. I'm sorry?
We're not in a poll.
Well, I like that, but no. It's the grammar exercise. Panda eats, shoots, and leaves. Does the panda eat 2 items of food, namely shoots and leaves, or after a lovely diet of shoots, or does the panda shoot and then after shooting somebody, leave? So depending on where you put commas, you can punctuate this very, very differently. There's a whole slew of sentences like that. I will send you a link of a Oxford comma lawsuit that cost a main dairy $5 million because of how the comma was put in and how you could then interpret deals with the union. You always want to think very carefully how are you writing things to try to maximize the understanding. And so when I was reading this first, I go, if f has no poles, well, if f has no poles, why am I subtracting off the number of poles of f inside C? Well, the reason is because the assumption is that we have no poles on C and we don't vanish on C. And so the proof of the argument principle is essentially just what we did over here. So over here, we just showed if we integrated f prime over f, we get n. So if there are zeros, if there's a 0 of order n at Z naught, we get a contribution of n. If there is a pole, so n would be negative, and if the pole is of order n, well, I guess the pole would be of order negative n, we would then get a contribution of n. And so the proof is essentially just using that argument principle. And so the proof, imagine, we have, as always, a nice region, Z1, Z2, and say Zn. And so what are we doing? We're integrating 1 over 2 pi I f prime of z over f of z. So we have 1 over 2 pi I integral over our curve gamma of f prime of z over f of z dz. And then we just play the game we always play. We come in, we come back. And so we reduce integrating over the outside curve to integrating over very small circles centered at each of these points. Since each of these circles is sufficiently small, we always have the expansion we had before, where there's only one thing that matters, the order of the 0 or the order of the pole. And then we just piece it all together. So this is the argument principle. So it's not immediately clear why we would care about this, but it relates this contour integral to some interesting information about f, the number of zeros inside the curve minus the number of poles. Why do you think we don't want to have a 0 or pole on the line that we're integrating about? We don't like dealing with functions that blow up on the contour itself. And so if we had a 0 or a pole on C, then we would have to figure, okay, now how do we deal with this? Or we have to maybe take limits, maybe principal values. What if we excise this and go inside or outside? It's much more complicated. It's much easier to just say we have a curve that does not have any zeros or poles on it. All right. So now Rouche's theorem. Suppose F and G are holomorphic in an open set containing a circle C and its interior. So as soon as you see in the book, it's saying a circle C and its interior, basically a nice region where I have the curve and I have everything inside the curve as part of my set. So I can really deform the curve and collapse it. And let's assume F of Z is always strictly greater than G of Z on this boundary curve. Then F and F plus G have the same number of zeros inside the circle C. So the first thing to note about this is you have to be extremely careful about how the result is stated. So I am saying this for function F and saying that F and F plus G have the same number of zeros. Sometimes people say the function F and the function H have the same number of zeros. And then you look at maybe H minus F. So depending on which book you look at, it could be slightly differently stated. It's not a big deal, but you always just want to be careful to make sure that you are using it the same way that the source does. And so here, I start off with some function F, I tweak it by adding a little bit to it. And we're saying on the boundary, the absolute value of F is strictly greater than the absolute value of G. So what can you tell me about F plus G on the boundary? So on the curve, what must be true about the absolute value of F plus G? It's not zero. Why is it not zero? I'm sorry? But maybe G could cancel F. So could G cancel F? F and G can't have the same absolute value because absolute value of F is greater than Z. So F plus G is greater than zero since the absolute value of F is greater than the absolute value of G on the boundary. So we do know that the absolute value of F is greater than zero. It is possible that at some point in the interior, F plus G is zero. But on the boundary, it can't be F plus G equals zero because the absolute value of F is strictly greater than the absolute value of G. So even if G and F have the same phase, have the opposite phases, have the maximum possible cancellation, it's not going to be enough to cancel. So we now have a function which is not zero on the boundary. And because we're assuming F and G are holomorphic, we know it has no poles. So what do you think might be useful to use? I'm sorry? Yeah, what we just did a few moments ago, right? Foreshadowing, right? We have a function which is not zero and does not have a pole on the boundary curve. Therefore, we know that this integral is the number of zeros minus the number of poles. So we can use the argument principle. For the function ft of z is f of z plus tg of z. And this is a great example of a deformation. So how many of you have seen something like this before, where I have a parameter t going from 0 to 1? So when t equals 0, I start off at f, and then I slowly increase f by adding some g of z to it. And when I get all the way to the end, I then have my final function f plus g. You might have seen this in linear algebra where you have two vectors, v1 and v2. And you might do t of v1 plus 1 minus t of v2. So in linear algebra, t of v1 plus 1 minus t of v2 goes from, I guess here, v2 to v1 as t goes from 0 to 1. So this is a way to deform from one to another, to slowly, continuously move. You can do this for curves. You can do this for so many things. Every now and then we have a technique. And when you have a technique, that's a trick that you can use more than once. That's something that's worth isolating. That's something that's worth remembering. And so we look at these functions ft, and now we use the argument principle. And that's where we get these NTs from. So NT is going to be the 1 over 2 pi I, the integral over C of ft prime of z over ft of z dz. What kind of number is NT? It's an integer. Did we talk about Benet's formula for Fibonacci numbers in this class? Okay. How many of you have seen Benet's formula? I know a bunch of you have. So if you see Benet's formula, it does not look like an integer. The nth Fibonacci number is 1 over root 5, go to the mean to the n, which is 1 plus root 5 over 2, minus 1 over root 5, 1 minus root 5 over 2 to the n. You've got square roots, you've got division by 2. It doesn't look like an integer. If I give you a generic function f that's holomorphic, this does not look like this should be an integer. It's a very severe condition to be an integer. Now, this is a function of t. If you want, I can write this as n of t to just emphasize that it is a function of t. What do you think we want to prove about this function? So it's continuous. So if continuous, then n of 0 equals n of 1, and we're done. Right, because if it's continuous, the only continuous function that's integer value is constant. No other continuous integer valued functions exist. So then why is this continuous? So continuous, it's 1 over 2 pi I, the integral over our curve of f of z plus t g of z prime, over f of z plus t g of z dz. And on the curve, we know that f of z plus t g of z is never 0. So the integrand is a nice function. So we're integrating a continuous function on a fixed curve of finite length. And so by just doing a little bit of analysis, it's a good exercise to go through and do this rigorously. This is going to be a continuous function in t. If I change t by just a little bit, because the integrand is continuous, I change the value by a little bit. So we see this is continuous. And so this finishes the proof of the argument principle. Yes?
Why did you write that to give us Reshade theorem?
Oh, because n of 0 is the number of zeros of just f.
Well, isn't it the number of zeros minus the number of poles?
Right, but I'm telling you, f and g are holomorphic, so they have no poles. So it's being very careful in terms of what I'm looking at. So we now have Rouche's theorem. If f and g satisfy this beautiful relationship, then we have this wonderful connection that they have the same number of zeros. So there's a bunch of things that Rouche's theorem implies. We will be doing these two, I think, in the next class. So I'm just stating them here as foreshadowing. So a mapping is said to be open if it maps open sets to open sets. And so one is the open mapping theorem. If f is holomorphic and not constant, then f is open. And we will see that this is very different again than what you would have in. Yeah, as soon as I say it's very different, you know the answer is real analysis. I mean, you don't even have to wait, don't wait for the buzzer. The next is the maximum modulus principle. If f is non-constant and holomorphic, then f cannot attain its maximum in the interior. The maximum has to be attained on the boundary. So that's really nice in terms of where do you need to look to find certain optimum So again, we are going to do a lot more on these in the next class. What I want to do now is just mention another application of Rouche's theorem, the fundamental theorem of algebra. And then just for being, different's sake, there's always the debate, which is better, Encyclopedia Britannica or Wikipedia. So today I chose to just paste from Encyclopedia Britannica. So a polynomial of degree n has exactly n roots when you count with multiplicity. Absolutely wonderful result. And then it's nice to have everything on the board, so I'm just printing or restating Rouche's theorem in the upper right corner, just so that we have that available to us. So what we need to do is we need to prove the fundamental theorem of algebra. And given that it says Rouche's theorem implies, we should probably use Rouche's theorem. So if we're going to use Rouche's theorem, what two functions do I have to define? F and G. Now, given that I have a polynomial, P of Z is an Z to the n plus an minus 1 Zn minus 1 plus dot 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 plus a1z plus a naught, I have to choose f of z and g of z. Somehow, the polynomial P better play a role in choosing f and g, right? Now, Rouche relates the number of zeros of f to the number of zeros of g. So either f or G, number of zeros of f and the number of zeros of f plus g. As other books I've read, it's f and h. So I have to constantly be correcting myself. So if we know the number of zeros of f, we know the number of zeros of f plus g. If we know the number of zeros of f plus g, we know the number of zeros of f. I need to find a polynomial where I can count how many zeros it has, say in a big circle, very easily. Anybody? Yes.
Oh,
Yeah. So something. So either f or f plus g is an z to the n. I'm just because an of course is not 0, otherwise I wouldn't have written. So do you want f of z to be an zn, or do you want f plus g to be an zn? Good. So let's try f of z equals an z to the n. But if this failed miserably, you would then pivot and say, let's try f plus g. So it's really nice when there's only two choices. The Seinfeld fans, what episode am I thinking of? Cultural extra credit. And there's only two choices. The opposite. When George Costanza decides to do the opposite of everything he wants, because all of his instincts are wrong, so the opposite must be right. If there's only two choices, try something. If it doesn't work, backtrack and try something else. The more choices you have, the worse this is. So we have f of z equals this. What should we choose for g of z? Well, the suggestion was try an minus 1, z to the n minus 1, plus a1z plus a naught. We somehow want to get p involved. And now we see f of z has n zeros in a circle of radius r, and f of z plus g of z is our function p of z, right? So if we choose a really large radius, will the absolute value of f be greater than the absolute value of g? Yeah. If CR is a circle of radius r centered at origin, if r is big, then the absolute value of f is greater than the absolute value of g on the circle. And the reason is the absolute value of f looks like an r to the n. So it's an r to the n versus say n times the maximum of the ak times the maximum of say 1 and r to the n minus 1. If you wanted to try to get a sense of how large can the function g be. Take the largest of all the coefficients, take the larger of 1 and r to the n minus 1, and then we have your n terms. So eventually, if r is sufficiently large, it doesn't matter how small an is and how large the other ak's are, I have a higher power of r. So as r becomes tremendous, this is going to be fine. Okay, well, what does that now mean? So by Roushay, f and p equals f plus g have the same number of zeros inside the circle. And there's the proof. So I think this is on the order of 5 minutes. What's nice is because I'm recording this, I can actually go back and see just how long did it take. This was a really fast proof of the fundamental theorem of algebra. I don't think this proof is in the book. This is another of the many, many proofs of the fundamental theorem of algebra. It does not use Liouville. Wonderful application of the argument principle. A great example of trying to figure out what's the right function to look at. And given that I'm trying to study this function P of Z, this polynomial, it's natural that P of Z should somehow be coming into play. The only way I'm going to have luck is one of my functions has to be nice to look at. So Z to the n or an Z to the n is the natural candidate for one of them. Yes.
Was there like a problem with this proof?
I don't think there's a problem with this proof.
Is the colloquium on Monday talked about like other proofs of the fundamental theorem?
Right.
They said, like, people said something about Gauss's like forgot something rigorous.
Well, this was not a proof by Gauss because this is using complex analysis. So this is post Gauss.
So I forgot it doesn't use level. It needs level for like the argument principle.
No, because Liouville is talking about a bounded entire function is constant. I'm sorry, we did not use that to prove the argument principle. You can double check, and if I'm wrong, let me know. Double check because I want to make sure we get to one last integration example. Well, because the function is f of z is an z to the n. So z to the n has a 0 of order n at the origin. With I can factor it as z times z times z times z n times. They were using that it has a 0 of order n. Yes. So check and see if we're using Liouville. Yeah. Right, and that we're not using. Right, in that part we were using. All right, so what I want to end with is integrating the function 1 over a plus cosine squared. We had remarkable success last time integrating 1 over a cosine x. Let's do cosine squared. If you feed this into Mathematica or Wolfram Alpha, they're cousins. You get out 2 pi over the square root of a 1 plus a. So this is another nice thing that we could do. How would you integrate this? What would you do? So what trick would we do? Okay, so we have cosine of z is, well, cosine of x is e to the ix plus e to the minus ix over 2. If the absolute value of z equals 1, then we get cosine of theta is equal to z plus 1 over z divided by 2. And we're writing now z as e to the I theta. So cosine squared of theta would be 1/4 z plus 1 over z squared, which is 1/4 z squared plus 2 plus z to the negative 2. Boy, is that so much fun to write with my handwriting. Right? And then dz is going to be e to the I theta I d theta. So dz is iz d theta. So d theta is 1 over iz dz. Right? And so we get the integral from 0 to 2 pi of 1 over a plus cosine squared of x dx is equal to the integral from 0 to 2 pi 1 over iz dz over a plus 1/4 z squared plus 2 plus z to the minus 2. And so, and then wait a minute, I was about to say, and now instead of doing here, this is now integrating over the absolute value of z equals 1. And that's the conversion we're doing. I don't have the 1 over 2 pi I, but I can put that in. So any questions about how we do this? Anybody have any other ways to do this? There is a better way. Yes? Well, because we're converting, we're writing z as e to the I theta. And as theta goes from 0 to 2 pi, this is the same as the absolute value of z equals 1, just going along that contour. So let's do trig. Cosine squared of x. Does anybody remember the double angle identities? Yes. Yes. So we know cosine of 2x is cosine squared of x minus sine squared x. Cosine x minus sine x sine x. So this is the same as 2 cosine squared of x minus 1, using sine squared as 1 minus cosine squared. So we get cosine squared of x is equal to 1/2 cosine of 2x plus 1, right? So that means our integral is the integral from 0 to 2 pi of 1 over a plus 1/2 plus the cosine of 2x dx. Now what can I do? Cosine 2x over 2. Yes. So I could do u equals 2x. So what would du be? 2 dx. And as x goes from 0 to 2 pi, what does u go from? Goes from 0 to 4 pi, right? So this integral is going to be the same as the integral u goes from 0 to 4 pi, 1 over, we have a plus 1/2 plus 1/2. Now cosine of 2x becomes cosine of u. And then dx becomes 2 dx. I'm sorry, du is 2 dx, so dx becomes du over 2. So this is the integral u goes from 0 to 4 pi du. Now when I multiply through by 2, I'll get 2a plus 1 plus the cosine of u, which should just be twice the integral u goes from 0 to 2 pi of du over 2a plus 1 plus cosine of u, if I've done it correctly. And what have we done? We reduced it to something we already know. So this is the Thoreau, the simplify. Before you start doing all this long algebra, which we can do, see if you can actually reduce it to something see if you can use your identities to rewrite it in a better way. This then tells you that there should be some connection between the integrals we get and the residues we get with the worst polynomial. Because when we do this, we're going to get a polynomial now that's going to be cubic, which is going to be a lot worse to work with in terms of factoring. And this is just going to be a quadratic. So I wanted to just do this example to illustrate that just because we have a technique doesn't mean we should always use it. Stop, pause, really think about what you have, and before you do any work, throw it. Simplify it and see, can I make it easier? And before I start working with cosine squared, I can rewrite it just involved the cosines. That's much better. All right, so I'm going to stop here.